Hello, and welcome to the Spiral webinar. Now allow me to introduce today's speakers and get this webinar started. Christy Jones has 25 years of experience with helping companies improve product quality, simplify the assembly process, and reduce costs through fastener and component design. During her tenure at Spiral, Christy has worked as an applications engineer, operations manager, North American sales manager, and is currently the vice president of marketing. Tara Mink is an industry expert in threaded inserts and compression limiters for plastic assemblies and has helped companies around the world design and implement innovative fastening solutions. Tara started her career at Spiral as an applications engineer in 2014 and is currently the product sales engineer for the Metal Cut Products division. Okay, over to you, Christy and Tara.
Hello everyone, and welcome to the Threaded Inserts and Compression Limiters for Plastics Assemblies webinar. My name is Christy Jones, and I'm the Vice President of Marketing and will be one of your presenters today. I'm joined by my colleague Tara Mink, our Product Sales Engineer for Machined Fasteners. Hello everyone. So I'll briefly go over what will be covered in today's webinar. We'll cover how to ensure continued integrity of a bolted plastic joint through the proper selection of threaded inserts and compression limiters. We'll go through the common types of compression limiters and inserts and the associated design guidelines for plastic components that use inserts and compression limiters. And finally, we'll go over the terms and concepts, recommended tightening torque, proof load, and clamp load. So a brief overview about Spiral. Spiral is a global manufacturer and supplier of engineered components used for joining, fastening, and assembly. We have 12 major product lines, each one designed to improve product quality, simplify the assembly process, and/or reduce the overall cost of the assembly. We're the only company who designs and manufactures both our engineered fasteners and installation equipment. Our focus, though, is not about just supplying high-quality product, but it's in working with our customers as early as possible in the design stage to help them design not only the fastener, but also make the critical recommendations between our product and their components so that their assembly goes together and stays together for the intended life of the assembly. And to accomplish this, we have applications engineers located around the world who are ready to work with you on your new or existing applications. So today, obviously, we're focused on inserts and compression limiters for plastics assemblies. So where are the inserts and compression limiters really used? Well, in short, they're pretty much used everywhere in every market, such as the automobile, agricultural equipment, rail, recreational vehicles, and they're also used in home appliances, medical equipment, hand and power tools, industrial equipment, and airplanes. They're literally used everywhere. Some of the specific applications within these markets can be seen here. In the top left, we have compression limiters used in the front engine cover so that when the cover is bolted down, these limiters provide spot reinforcement to prevent the plastic from cracking. Next, you can see compression limiters in an intake manifold and compression limiters in a residential charging connector for solar-powered homes. In the lower left-hand corner, there's an example of threaded inserts used in a high-voltage switch assembly. An oven handle where the bolt is threaded directly into the metal insert rather than into the plastic to ensure joint integrity over the life of the assembly. And finally, you can see an automatic pool cleaner housing that has literally dozens of inserts on both sides of the component. Moving on to some of our important terms. When discussing the performance of our compression limiters and threaded inserts for plastic, it's important to tie them back to the component that designers are typically more familiar with, the bolt. Bolt performance is defined by an industry specification that outlines how much force the fastener can withstand before breaking. The proof load is the maximum load that can be applied to the bolt without risking permanent deformation, where the bolt will not return back to its preloaded condition when the joint is loosened. Excuse me. The clamp load is really how much load is applied to the bolt when the joint is tightened. Spiral recommends that a joint is tightened to the clamp load up to 75% of the proof load because the bolt's load directly is related to the torque that the manufacturer applies when using a wrench or a torque gun.
The amount of load that a bolt can withstand is typically defined by the thread size and the grade for inch bolts, or the class for metric bolts. These are the most common bolt specifications defining bolt strength.
So why do people use threaded inserts in plastic? Well, first and foremost, inserts provide reusable threads and secure tight threaded joints. Since you thread directly into metal rather than into plastic, you have unlimited assembly and disassembly without fear of stripping the threads. You're also able to meet the proper seating torque for the bolt, given that the integrity of the plastic is there. And unlike when you thread directly into plastic, you do not have to worry about stress relaxation or creep that could result in a loose joint. And finally, given that the OD of the insert is approximately 2 times the OD of the bolt, this results in 4 times the shear surface for enhanced load carrying of the bolted assembly. Before we talk about what types of inserts are good for particular applications, we first need to review that there are 2 major types of plastics: thermoplastics and thermosets. Thermoplastics essentially can be melted and remelted a number of times into a number of different shapes without compromising the mechanical properties, whereas thermosets have a one-time reaction from liquid to solid and cannot be remelted. Both thermoplastics and thermosets can be strengthened, though, through the use of glass or mineral fillers. Usually the higher the percentage of filler, the stronger the plastic.
Spiral threaded inserts are categorized by the primary method of installation. Some inserts are designed to be molded into the plastic when it's fluid. This lets the molten plastic flow around and into the more aggressive features on the outside of the insert. Most inserts are designed so that they can be installed as a secondary process after the plastic is cooled. These are referred to as post-mold installed. Post-mold inserts can be installed a variety of ways, by either locally remelting the plastic, by pressing them into the plastic holes, or even by screwing them directly into the plastic. Inserts should be designed with sufficient torque resistance to accommodate the tightening torque required for the bolt to prevent loosening and to achieve the pull-out values necessary for the load conditions that the insert will be exposed to while in service. In general, the resistance to rotational torque is the function of the insert's diameter, and the resistance to pull-out, also known as tensile, is the function of its length. The designer's challenge is to determine the best balance between these 2 design criteria and optimize the performance in the space allotted.
The internal threads of the inserts are designed around industry standard metric and inch bolts. As far as the external features of the inserts go, essentially, performance of the insert is generally achieved based on the amount of displaced plastic filling the various types of features of the insert. There are typically 3 different types of knurls: diamond, straight, and helical, and they are primarily used to increase resistance to torque. Straight knurls have the best resistance to torque since they're perpendicular to the force, whereas helical knurls provide resistance to both torque and pullout as they're at an angle. Finally, diamond knurls, frankly, they're just not great for much of anything. The reason being that if you press a diamond knurled part into plastic, the diamonds literally shred the plastic during insertion. The most popular type of insert where you see this diamond-style knurl is on what they call an expansion-style insert, shown here in the upper left. As the insert is pressed into the plastic hole, the slot closes. As the bolt is installed into the internal thread of the insert, the bolt ends up opening up the insert and pushing the sides of the insert against the hole wall, such that the diamond knurl bites into the hole wall to hold the insert in place. However, reality is performance of this style insert is pretty low, yet the cost is much higher than most other styles of inserts. As a matter of fact, Spiral has since replaced the expansion style insert with other press-in styles that have much higher performance at a much lower cost. Other performance features are barbs and undercuts, as shown on the insert in the bottom right, where the displaced plastic flows into the undercuts, and then the barbs help prevent the insert from pulling out of the plastic. So there are many different types of inserts, and in order to specify the best insert for a particular application, it's critical to understand the plastic specifics, meaning not just whether it's a thermoplastic or thermoset, but what specific type of plastic it is and what percentage of filler it has, and if possible, the brand name of the plastic. So as an example, GE Cycloid C2950, which is a PC ABS blend with 0% fill, or perhaps you're using DuPont Nylon 66 with 30% glass fill. We also need to understand the geometry of the host component, including available space for the hole diameter and wall thickness, what bolt size you are planning on using, as well as the grade or class. This is super important because, as Tara reviewed earlier, the class or grade actually dictates what the recommended tightening torque is for that size bolt. We also want to make sure that we understand what the performance requirements are for the application, the torque and pull-out or tensile, and what the mating component configuration is. And finally, how do you plan on installing the insert? Will it be molded in or post-mold installed? And if post-mold installed, will it be simply pressed into the assembly, heat ultrasonically installed, or tapped into the hole?
So as Christy alludes to, there are many factors besides insert design that impact how the insert will actually perform in the application. The quality of the interface between the insert and the plastic component is so critical to how much the insert can withstand rotational loading and axial loading. Installation also greatly impacts the quality of this interface. It's been set up to 75%. The image to the right demonstrates how Spiral actually recommends validating installation quality through a destructive test. We recommend cross-sectioning the plastic with the insert installed so that you can see the interface between the insert and the plastic. There should not be any voids present between the insert and the plastic. Then, the insert can be removed from the plastic, and you should be able to see a mirror image of all of the insert's features in the piece of plastic. As you can see in the incorrect example, the knurl's imprint in the plastic was very shallow, and there's no evidence that the barb actually engaged the plastic. Some common errors that lead to poor installation are listed to the left, but in this example, you can see that there was probably an incorrect hole size that was too large, not allowing enough plastic to flow into all of the insert features. And it's not just that interface between the insert and the plastic host component that are critical to performance. The mating part also can significantly reduce performance by not providing enough of a bearing surface on the insert, which we call a jackout condition. With the hole size and the mating component larger than the face of the insert, there's nothing we can do to prevent the insert from dislodging and moving up into the void of the mating part. To avoid jackout, we recommend that the mating component's hole is smaller than the face of the insert, but large enough so that the the bolt can pass through.
I'm sorry, Tara.
That's okay.
When installing the insert into the hole, the top of the insert should be as close to flush with the surface as possible. Maximum protrusion above flush should be 0.13 millimeters or 5 thousandths. And you really want to be careful about having the insert subflush, or else you risk jacking the insert out of the hole, or at least breaking the plastic plane while torquing down the bolt, which could affect joint integrity. In terms of the hole configuration, the diameter of the plastic around the hole, known as the boss diameter, should be sufficient enough to avoid bulging during installation and ensure integrity to withstand the recommended tightening torque. Also, the length of the hole must be long enough to prevent the screw from bottoming out in the event that it's a blind hole. For heat or ultrasonic installation, the length plus 2 thread pitches is recommended to allow any flash or material buildup ahead of the insert a place to flow during installation.
The actual hole size is also critical to the insert's ability to perform in the assembly. For inserts used in a straight hole, it's recommended that the taper does not exceed 1 degree inclusive or ½ degree per side. For inserts intended to be used in a tapered hole, the taper should be 8 degrees. The greater taper not only assists with removal of the plastic component from the mold, but it also allows the insert to sit deeper in the hole, which facilitates square insertion and faster installation. Regardless of hole style, it's imperative to hone in on the correct hole size for the application. As a general rule, Larger hole sizes decrease performance, while smaller hole sizes induce undesirable stresses and potential cracks. Spiral's recommended hole sizes in our design guideline will typically need slightly positive adjustments, if any. Usually, the hole size needs to be adjusted upwards when the melted plastic is more viscous and it does not flow very well, such as when fillers like glass are used. It is always imperative that the designer perform testing to validate the appropriate hole size for the application. Spiral is also capable of assisting with this testing. Just to show an example in the lower right, if there's no filler used, such as like a polypropylene plastic part, the recommended hole size for our M6 heat-installed insert is 8 millimeters with a positive 0.08 millimeter tolerance. However, if the same component was nylon 6/6 with 35% glass fill, we would adjust this initial 8 millimeter hole recommendation up by 0.15 millimeters and then apply that 0.08 millimeter tolerance. The core pin used to mold the host hole should be large enough to allow for the plastic to shrink down once cooled and conditioned. The plastic hole size should then be verified with a plug gauge once the plastic's cured, but prior to inserting the insert so that any adjustments can be noted against this benchmark.
In high-load applications, using a headed insert and locating the head opposite the load in a pull-through configuration warrants design consideration. That said, tapered inserts should never, ever be used in pull-through applications or in thin-walled boxes, as this will definitely cause cracking of the plastic. Each type of insert differs in design, which yields different performance results, as well as the cost of the insert and overall cost of the assembly. Starting with heat or ultrasonic inserts, some are designed for straight holes and others are designed for tapered holes. If you attempt to use a straight insert in a tapered hole, you will not optimize the performance of the insert design, and in many cases, you may end up totally cracking the plastic. Symmetrical inserts require straight holes, and as Tara just said, tapered holes facilitate proper seating of the insert, and since the surface contact between the insert and the hole is maximized, installation time is usually less than that of a straight insert of the same size. Many heat ultrasonic inserts are available in a long and short version of each thread size. Long lengths maximize torque and pull-out resistance, while short lengths are good for less stringent requirements at a lower cost and shorter installation times. You can also get most styles with or without a head. The head provides bearing surface for the mating component that also prevents jackout, or, as I said earlier, when used in reverse, can prevent a pull-through situation. However, adding a head comes at a cost because you have to start with a larger piece of raw material to create the head. Now, some non-headed versions are symmetrical, thus eliminating orientation during the installation process. You can achieve excellent performance results with heat or ultrasonic inserts, provided that they are used in the proper hole size with sufficient wall thickness around the insert, and they are installed in a manner that results in proper melting of the plastic to fill the voids of the insert. Heat ultrasonic inserts generally provide the best balance between performance and cost. Now notice the external thread on the self-tapping inserts. This type of post-mold installed insert is actually threaded into the hole after the plastic cures. The external threads are designed with a thin profile to minimize stress in the plastic and a relatively coarse pitch to provide the maximum plastic shear surface to resist pullout. As a matter of fact, these inserts provide the best resistance to pullout of any of Spiral's post-mold installed inserts. However, due to the external thread, the manufacturing cost of this insert tends to be higher than other types of inserts, and the cost of installation is the highest of all post-mold installed inserts, since care and time have to be taken to thread the parts into the hole. The schematic in the lower right shows that the recommended length of the hole for this style insert is 20% longer than the length of the insert. Counterbores are not recommended for any insert types except self-tapping and headed inserts. Counterbores are recommended for self-tapping inserts to reduce the risk of flaking. The outside diameter of the counterbore should be equal to or larger than the outside diameter of the self-tapping insert.
Press-in inserts are designed to reduce installation costs. Helical knurls provide both torque and pull-out resistance. A pilot facilitates straight insertion into the hole. The pilot diameter is only slightly smaller than the hole, and the length is long enough to allow the insert to sit at the top of the hole prior to installation. Crescent inserts are available with or without a head and provide good resistance to torque and pull-out. They are a great low-cost option for applications not requiring super high performance. On the other hand, molded-in inserts are designed for maximum pull-out and torque performance and are often the insert of choice for thermostats and engineered plastics with a high percentage of filler. The minor thread diameter tolerance is controlled to provide a repeatable fit on the insert on the core pin, and Spiral offers a symmetrical version, eliminating the need for orientation, and a blind-ended version, which sometimes is preferred by molders. Unlike the rest of our brass inserts, these are made from 2024 aluminum, a lightweight, lead-free grade.
So in terms of using post-mold installed or molded-in inserts, there are many factors to consider. Installing inserts after molding reduces in-place cost as the molding time is shortened since there is no placing of the insert over core pins. Secondary cleaning of flash or plastic around the entrance to the hole that often occurs with molded-in inserts is also eliminated. Installing inserts after molding also reduces rejects and the chance of mold damage resulting from a dislodged insert. And keep in mind that some of these molds cost tens of thousands of dollars. And finally, a post-mold installed insert can yield excellent performance results. Conversely, when molding inserts into the assembly, the molding time is increased as you have an operator or a pick-and-place robot loading the inserts over the core pins prior to being able to close the mold cavity. Also, precise placement of the inserts is required, otherwise mold damage can occur, which can be really expensive since molds are expensive and so is downtime. That said, of all of the different types of inserts, you definitely get the best performance out of molded-in inserts. So the question really is, what performance do you actually require for your assembly?
So one question we see all the time is what affects the performance of an insert? The fact is there are so many variables that impact insert performance in an application. Not only the insert design and the quality of the features such as the knurls, bands, and undercuts, but also the specific type of plastic will generally affect performance. For example, an insert installed in nylon 6/6 with glass fill will totally outperform a talc-filled polypropylene. Also, the design and quality of the plastic molded part plays a huge role in performance. For example, are there knit lines in the boss surrounding the insert, or is the wall thickness of the plastic sufficient to handle the applied stress? Obviously, the actual hole size will also affect performance. Even hole size variation within the recommended tolerance range can impact performance greatly. And finally, the installation quality impacts performance. For example, was the proper temperature used? Were the inserts installed too quickly? So on and so forth. In regards to temperature, another question we often get is what temperature should heat-installed inserts be installed at? We recommend starting with a temperature of 50 degrees Fahrenheit above the initial softening temperature for the plastic in question. For plastics with fillers, this initial differential should be increased to around 150 degrees. Pressure is insert size dependent and should be as low as possible in the 5 to 15 psi range. The pressure should be just enough to push the insert into the hole as the plastic melts.
So how do you know if you have a properly installed insert? This is most definitely a destructive test and maybe even a little barbaric. We would literally take a hacksaw and section the plastic component with the installed insert, section it in half, then pop the sectioned insert out of the hole and ensure that the features of the insert are mirrored in the plastic as shown in the image on the right. It's extremely important to ensure proper plastic flow into the features of the insert, as this dictates the torque and pull-out performance. As you can see on the left, the plastic did not sufficiently flow into the retention features, which will result in low insert performance. And this by far is the most common question. How much torque or tensile strength can be achieved in my particular application with my specific plastic assembly? And the reality is it's impossible to answer without testing in your actual assembly. Of all of the factors that we just went through a couple of slides ago that affect performance, and in addition, there are just so many different types of plastics and fillers, and then percentage and orientation of those fillers within the plastics, coupled with the complexity of component design, it just makes it impossible to provide insert performance data which can be applied to specific applications. Spiral provides a section in our design guide that displays the performance of various style inserts installed into nylon 6/6 without fillers in drilled versus molded holes. There's a screenshot of that on the slide right now. The performance data here is provided as a comparative guide between insert types, not to provide the actual performance that will be achieved in a specific application. For this, you will definitely need to test.
Now let's talk about compression limiters. Just so you know, this section is going to go a little bit quicker because a lot of the same concepts apply than when you're talking about the insert.
Woohoo!
So what are compression limiters? Essentially, compression limiters are spot reinforcement of metal in a plastic assembly designed to protect the plastic from cracking or yielding under the compressive load of a bolt. Essentially, in a bolted jointed assembly, the objective is to not stress any component beyond its elastic limit. The ability of the compression limiter to carry a compressive load is determined by two factors: the strength of the material and the cross-sectional area of the compression limiter. Limiter strength can be increased by increasing the wall thickness, increasing the strength of the material or the type of the material, or a combination of both of those.
There are two critical design conditions to consider when using any compression limiter. Rule number one is that the bolt or washer must contact the compression limiter. This condition must be met without exception. If the bolt does not contact the limiter, it will result in plastic creep and ultimately loss of compression over time. Now, the image on the right would not be acceptable if the bolt was fully torqued down. In this case, the compression limiter isn't doing anything at all. It's just adding cost to the assembly with no value. The image on the left shows a proper bolted joint.
Rule number two, and it's more of a guideline, is that the plastic should have a small amount of compression. If the plastic is not compressed, the host component could move up about the compression limiter. And by the way, it's important to note that the delta showing the gap between the bolt flange and the limiter only exists prior to torquing the bolt down. Once the bolt is tightened, the plastic has to be compressed to get the metal on metal on metal contact Christy just mentioned. That's non-negotiable.
So in order to properly evaluate an application and determine the most appropriate compression limiter, the following needs to be understood. It's important that both the bolt size and the class or grade is known, as the class or grade will dictate the recommended tightening torque, which ultimately determines how much force the compression limiter must withstand. And by the way, we're hammering that home because we'll often get M6 bolt and we don't have any idea what the class is for that bolt. We also need to understand the max allowable compression of the specific plastic. Now, most plastics can compress between 5 and 15%. The plastic thickness and compression limiter length tolerances are also very important, as ideally we would like to have the maximum compression limiter length be equal to or below the minimum thickness of the plastic without exceeding the max compression of the plastic. See how these are intertwined? The yield strength of the mating component is also important, as we want to make sure that you don't indent the material of the mating part, creating witness marks when the bolt is torqued to the recommended tightening torque. And finally, we want to understand the environment to which the compression limiter will be exposed, as well as the specifics of the material of the mating component, so that we understand both the environmental and galvanic corrosion requirements.
So here's an example of how we use some of the information that we just talked about. If we don't have any information about the plastic's modulus of elasticity, we'll typically assume a conservative compression amount of 3% of the plastic. In this example, the customer is early in the design stage and has selected our M6 by 20 millimeter long compression limiter, and they're looking for our feedback on the plastic thickness tolerance. Now remember, there are two rules for compression limiter length as it relates to the plastic thickness. The compression limiter must bottom out against the mating component and the bolt's head or washer once the bolt is tightened. And ideally, the plastic has a slight amount of compression when the bolt is tightened. To try to achieve both of these design criteria, the maximum compression limiter should be equal to the minimum plastic thickness. In this example, we know that the length of the compression limiter is plus nothing with a minus 0.15 millimeter tolerance. Since we want the minimum plastic to be 20 millimeters, which is the compression limiter length, we would want to assign a positive tolerance on this plastic. In this example, we're assuming that the molder can maintain a 0.1 millimeter tolerance. Now that we know this, we can calculate the stack-up tolerance to be 0.25 millimeters. If we compare the stack-up tolerance with the allowable compression, or 3% over 20 millimeters, which is 0.6 millimeters, we could see that the stack-up tolerance is not going to be a problem as it's less than the amount that the plastic can safely compress. Now to tie in the rest of this information that we just discussed. This scary-looking equation is how you calculate whether or not the bolt is strong enough to compress the plastic. For time considerations and to make sure we don't put anybody to sleep who's listening, I'm not going to go through the details of this calculation, but it will be included in the presentation that will be emailed to you within a couple of days of the seminar.
So in terms of selecting which type of compression limiter is best for your application, there are a variety of compression limiters available, usually designed around standard bolt requirements and the method of installation. The overarching difference between the different types that we're going to talk about are the limiters that are rolled from steel and those that are machined from aluminum and brass. Within the rolled form steel category, we offer a split seam for post-mold installation or a butted seam for molded in. These are offered with an oval shape to accommodate a wider tolerance in one axis for easier alignment, just another option. Which is basically particularly useful when you're using multiple limiters in an assembly. Within the machine category, these can be installed either by pressing in or molding in. You don't need to specify a particular machined version to match the installation method. A head can be added to increase the bearing surface against the mating component or the bolt. Unless there's a concern with galvanic corrosion, aluminum is generally preferred over brass because it's lightweight, lead-free, and stronger than brass. And in terms of how to choose between machined or rolled form limiters, the reality is that when it makes sense, rolled steel is definitely the most economical option. However, for short compression limiters, particularly when the length to diameter ratio is less than 1, it makes most sense to use a machined limiter because it's difficult to roll a limiter that short and keep the end square. Also, machine limiters are preferred in mold-in situations where the plastics have a very low viscosity since there are no seams for the plastic to seep into. Machine limiters can be supplied with a head for larger bearing surface for soft mating materials. A head also eliminates a washer. However, the best option is to use a flange bolt instead. Finally, if you're going to use a machine limiter, we recommend aluminum over brass again, since it's lighter and stronger than brass and it's lead-free. As I said a few minutes ago, rolled steel limiters are less expensive and they can also be heat treated to withstand higher tightening torques. The split seam is designed such that the part is pressed into the assembly, whereas the butted seam is suitable for molded in with viscous materials. Also, as we mentioned in the last slide, the rolled steel versions are available in an oval configuration for extra clearance on one axis, as can be seen in this application in the lower right of this slide.
To summarize the design considerations for compression limiters we just covered, our most important criteria is that you get that metal on metal contact, or the bolt flange on compression limiter on mating component contact once the bolt is tightened. Remember, without this, you're adding costs to the assembly with no value. Then, ideally we want some plastic compression where the host thickness is greater than or equal to the compression limiter length. The plastic must be able to withstand the clamp load of the bolt without exceeding its elastic limit. If this is not possible, we're happy to offer a recommendation for how to optimize your joint and still achieve that critical metal-on-metal contact. Just like the plastic, we also need to make sure that the bolt does not exceed the elastic limit by assigning a clamp load up to 75% of the proof load. If an insert is used, like in this example, the limiter should be well aligned to prevent a jackout condition. And lastly, the host hole size is critical to ensure the compression limiter can retain its position in the host prior to bolting the assembly.
So in conclusion, think about inserts and compression limiters as early as possible in the design stages of your project. This will help you design in standard components, which reduces time and cost since they can likely be supplied from stock. Also, don't over-specify your requirements. If you say to a manufacturer, just give me the insert with the highest torque and pullout, when your assembly doesn't require high performance, you're going to be paying a lot more for something that you actually need. When designing your assembly, use the proper design parameters, and please do yourself a favor when switching from one supplier to another. Provide the actual performance you require for your assembly versus saying, just give me the same or higher performance than I'm getting right now with my current parts. And recognize that if you ask one manufacturer to make the exact same part as what someone's already making, you're usually going to pay more from the new manufacturer because they're not set up to make that part. And finally, after all is said and done, make sure to test the bolted assembly to ensure that your performance requirements are met. If you're interested in learning more about inserts and compression limiters, I encourage you to visit spiral.com and download the application stories and white papers. And also, we do have 3D models available from our website that you can download or insert directly into the model of your assembly. If you're working on a new design, involve Spiral as early as possible. We'll conduct a comprehensive evaluation of your application, then provide you with a detailed engineering report complete with samples for testing and approval, provided that we can equip you with a standard component. At that point, I think I'm going to turn it back over to Megan.
Okay, thank you, Christy and Tara, for your great presentation. We do have some time for some questions, so let's get the Q&A session started. Okay, our first question is, why doesn't Spiral manufacture inserts out of plain steel?
Thanks, Megan. So, despite the cost of steel typically being less expensive than brass or aluminum, it is difficult to machine and it chews through tooling quicker than brass or aluminum would. Also, steel inserts typically require some kind of plating for corrosion resistance, which further increases the cost of the insert. And potentially, there are also, quality defects that could occur with plating a threaded part. Not to mention the potential of mixed product due to the plating process.
Okay, thank you. Our next question asks, can I use a soldering iron to install inserts?
Good question, and we do see this. Technically, you could, but it's most definitely not a good idea. You won't get a repeatable insertion depth. You'll likely not install the insert square into the hole, and you won't have control over pressure. And also, many soldering irons, and I know there's a variety of different soldering irons out there, but a lot of them are not available with a variable temperature setting. So you most likely will be installing with the wrong temperature.
Okay, thank you. Our next question asks, is there a rule of thumb for minimum or maximum number of molded part volume when it makes sense to use molded in versus post-mold inserts, thinking for system assembly cost optimization?
Thanks, Megan. So I would say that this really, depends on the molder's preference as to whether or not they would prefer to, mold in multiple inserts or take that process offline. Spiral does, provide a full set of installation, automated installation equipment, and we do have the ability to install multiple inserts N1 time. It's called our platen style insertion equipment. But depending on, how many inserts you're looking to place into the mold, and how much it impacts the cycle time, it really is going to be something that, as far as like coming up with a number of inserts, is up to the molder's preference, I would say.
Just to add to that, usually volume dictates whether it should be machined or rolled if you're also looking, considering molding in, because we do have options in both, and other manufacturers do as well, where you can have machined molded in or rolled molded in. And we do have some kind of a threshold that's typically where we're looking at for
compression limiter specifically, you mean?
Like,
yeah.
Volume around it. Once you get over 1 million.
Yeah, maybe even a little bit more. It might be more cost effective to look at a compression limiter that's rolled.
Okay, thank you. Our next question asks, length was mentioned as being proportional to pull-out resistance. Is a longer insert naturally more resistant to a pull-out, or is it that a longer insert can have more undercuts designed into the external geometry?
Let's see, sorry, I'm just rereading the question here. Well, with a longer insert, you have more features for the displaced plastic to flow into. And like we mentioned earlier, a lot of times you can get a long or a short version of the same style insert, and it really does boil down to this: how much performance do you require out of that insert?
Okay, thank you. Our next question asks, do you have published documentation on your website for insertion force requirements of press-in compression limiters?
We don't. And the reality is, similar to what kind of performance am I going to get out of an insert or compression limiter, the reality is, due to the variables and the great number of variables, we really do need to test in an assembly. Sometimes when customers are in the design stage and they know what kind of plastic they're going to use, and we're kind of narrowing down what the length of the hole is going to be, you can test in plastic pucks that sort of represent your molded part without actually having to mold the part itself. But we don't, just because of the variety of different materials and all the variables, we don't have any published documentation. And if we did, it probably wouldn't match your specific application. So if you see any, just know that those results are when tested under certain parameters and exact parameters.
Okay, thank you. Our next question asks, what is the main concern with witness marks? Once it is assembled, does this affect the performance?
So just, a witness mark is something that, when the mating component of something such as like a compression limiter joint, the threaded component being the mating component, if that's not a material that has enough strength to withstand the loading through the wall of the compression limiter and that surface area, you could have some slight, permanent movement or an indentation of the material. Typically, if it's only slight, it won't really impact the performance once the product's assembled, assuming that the mating component is a steel and that you're not adjusting the load once it's, bolted down.
Okay, thank you. Our next question asks, how much material is generally required around the insert?
So we do have a general rule of thumb, and that is that the boss diameter be 2 times the insert diameter. That's the rule of thumb. Sometimes people ask, well, what if I can't get 2 times the insert diameter? The reality is, we're giving the design guidelines as ideal conditions, So it's not that it won't work, but that is the ideal design. Is the boss diameter is 2 times the OD of the insert.
Okay, thank you. Our next question is, when heat stacking an insert, how can I prevent float?
So when you're heat staking an insert, float is typically, when the insert wants to, rise above the melted plastic, and it actually literally floats because the plastic is still molten. Typically what we would recommend is that you actually hold the heat tip down, for a certain amount of time, just to make sure that, the insert doesn't start to lift up and float and it becomes almost proud in the plastic when you're doing a heat insertion.
And keep in mind that if it's floating too much, you might be using the wrong temperature. So as Tara said, usually there's a stall with a heat inserter. So it installs to the depth, it stalls for a couple seconds,
right,
and then it releases, the weld time, and then it releases. But if you're getting too much float of the insert, I would definitely double check the temperature settings.
Okay, great, thank you. Our next question asks, can you talk about inserts that are open on both ends? For example, a power terminal / contact.
So most of our inserts do have a through hole, or they're open on both ends. Typically we have these inserts, primarily for post-mold and installed, applications. However, we do have customers, and we do have a standard offering of mold-in inserts for, through hole inserts as well. Typically what is done is there would be some sort of either some feature in the mold, whether it just be the other side of the mold that contacts both ends of the compression limiter, or the insert rather, to close the thread off and prevent any plastic from getting introduced in there. Or sometimes if the thickness of the plastic is different than the insert length, a through plastic hole would be molded by having another core pin mate against that through hole insert.
But again, just to add to that, the majority of the inserts with through holes are post-mold installs.
Right.
I just want to make that clarification, because when we're talking about closing off or clamping off the molds, we're talking about molded in inserts.
Good point.
But if we didn't answer that question, but if you have more of a follow-up, please send in another one, because we're not exactly sure if we covered what you wanted us to get at.
Okay, great, thanks. Our next question asks, do you offer compression limiters larger than M8?
So we do. We do have a standard and stock line of M10 compression limiters with the split seam available as well, and then also a 3/8 size. But we, as far as other options other than just that split seam, we do have designs that are created. It's not a product that we hold inventory of at this point. It's not part of our catalog standard offering, but we do have a design already created for M10 typically.
Okay, great, thank you. Our next question asks, is it necessary to have an O-ring when the application has liquid on one side?
So we don't get into a lot of applications where you need to seal liquid from an assembly. I mean, that's usually done by the designer. And honestly, I don't think we're really prepared to answer that question, because the answer would probably be yes. And I know, by the way, you can get some inserts that have an O-ring actually pre-installed onto, the pilot of the insert, but we don't really get into many types of applications. That being said, our inserts are used in applications like pump housings, where there is liquid that flows through there, where they're not really concerned about sealing per se.
Okay, great, thanks. Our next question asks, what installation methods result in the least amount of particulates being generated?
Well, molding in, obviously, you're not going to get any particulates from the insert or compression limiter. At that point, you just have to be concerned about flash that's left around the entrance to the hole. Otherwise, you really shouldn't get particulates. I mean, the parts, you should be buying from a manufacturer that has clean parts. So even when you have internally threaded inserts, under ultrasonic insertion, you shouldn't be having chips that are coming out of the insert in the assembly. That being said, if I were to compare ultrasonic versus heat installation of inserts, I will say that you do see damage more often most often with ultrasonic installation, and it mostly boils down to you have to be really sure that your assembly is clamped appropriately so that you don't get any external vibration of the assembly that is then translated onto the actual insert. And you also have sometimes the horn will cause damage to the top threads of an insert when ultrasonically installing parts.
Okay, thank you. Our next question asks if you can please explain split compression limiters calculation for plastic hole size versus OD of compression limiter OD.
So typically, the hole size for a split seam compression limiter is going to be slightly smaller than the listed OD in our catalog for a split seam compression limiter. The reason being, we want the compression limiter to actually be sized by the hole, and the OD would effectively decrease as you install the split seam compression limiter into the hole. This will allow the compression limiter to retain its position in the plastic before you bolt it down, with some spring force, so by sizing the compression limiter.
Okay, great, thanks. Our next question asks, my applications with compression limiters will involve knit lines. How will this affect the performance?
So typically, a knit line we typically see that they negatively impact the performance if they're around the boss of where the insert's going to be used, because we'll typically see that when applying the load to the insert, that's typically where the plastic will crack. So that's why when we are doing testing, or when a customer is doing testing, we would recommend that you look for any knit lines and see if there's any correlation between once you're actually applying the stress to the insert and the plastic part, if cracking occurs at a knit line.
This is even more prevalent when you're talking about thin-walled bosses too, because it is a point, like Tara was saying, it's one of the primary points of failure if we see failure in an assembly. So I know you sometimes can't avoid the knit lines. The question is, I don't know if you can gate, and I'm not a molder, but can you gate it differently where you minimize the knit lines or move? You can try to move the knit line from where the hole is located.
Okay, great. Thanks. We have time for one more question, and that question will be, what is the max allowable draft in the plastic parts holes when using post-mold limiters?
So we would say typically the maximum draft that we would like to see when using a post-mold compression limiter is going to be that 1 degree inclusive angle. However, I will say that for some of the longer compression limiters, which typically, we're talking about the split seam style, it is imperative that at least 60% of the limiter's length is within the recommended hole tolerance. And sometimes even with the 1 degree taper, if you're talking about a compression limiter that's, a couple inches long. Sometimes that can present a challenge. So typically, though, as a general, that 1 degree is a good rule of thumb.
Okay, thanks. And with that, we're going to wrap up this webinar right there. Thank you to our presenters for spending some time with us today, and thank you to our audience members for being a part of this webinar event. Take care and enjoy the rest of your day.